Okay, let's look at that again. So let's look at different cases when both the solute and the solvent are polar. What happens in that case? Well, both substances have got electrostatic forces of attraction, so the positive and the negative is attracting on the solute and the solvent side. It really doesn't matter which one we call the solute or the solvent. Remember, that goes back to the definition. So whatever is in the lower amount would be the solute, whatever is present in the higher amount would become the solvent. So A or B could be either. When A and B mix in solution, you have similar forces of attraction, so that is what is the driving force for the solute to dissolve in the solvent. So let us look at the special case of water, where water is the solvent. So again, going back to unit 1 when we were talking about the shape of the water molecule. So we've got the oxygen in the middle, water has a bent shape, and then it has two lone pairs of electrons. Okay. So water tends to have a delta negative and the delta positive end. So that's the shape of the water molecule. How does this help water dissolve polar solutes? So let's think of a polar solute. I don't know if there's an example here, but let's say sodium chloride. So you've got the sodium ions and you've got the chloride ions. And again, this is in a rigid crystal lattice arrangement. Just for the ease of depicting in a diagram, I'm only taking one ion each, but that's not the case. So each sodium ion is surrounded by 8 chloride ions. Each chloride ion is surrounded by 8 other sodium ions. It's hard to draw for me, but I think your textbook has a nice picture of the sodium chloride dissolving in water. So when this goes into water, again, you don't just have one water molecule, you have a few water molecules, each with a delta negative, delta positive ends. Okay, so when this goes into solution, the sodium, the positive sodium ion, gets surrounded with the oxygens, which are the negative end of our water molecule. Okay, so this is okay, whereas the negative chloride ion would get solvated or surrounded by the positive ends, by the hydrogens. Oh, sorry. Hydrogen, hydrogen. And as I said, sodium chloride will dissolve in water only if this interaction of the sodium ions with the water molecules and the interaction of the chloride ions with the water molecules releases more energy than is required to overcome this interaction of the positive sodium ion with the negative chloride ion and the hydrogen bonding between these water molecules, right? So this is the AA interaction, BB interaction, and we are talking about the AB interaction here. So this compound dissolves in water only if this interaction releases more energy than is required in overcoming these two interactions. You would write this process in an equation often as, so sodium chloride solid dissolves in water. So the condition is written on the top of the arrow to form aqueous sodium ions, AQ, and aqueous chloride ions. Okay. Another term that I guess I should have made space for that, a set of terms that sometimes cause confusion is dissociation and ionization. Ionization is when something that does not exist as ions earlier, so maybe it's a polar compound, which becomes an ion when it dissolves in water. Whereas in the case of sodium chloride, you already have ions present. So when sodium chloride dissolves in water, this is not ionization. This is dissociation. So the sodium and the chloride ions are disassociating and forming the sodium ion aqueous and the chloride ion aqueous. So this is dissociation. It is not ionization. An example of ionization would be something like hydrogen chloride. So hydrogen chloride gas dissolving in water would produce new ions, the H plus ion and the chloride ion. So that process is ionization. We will talk about that again later. So let's look at how ionic size and ionic charge affects the solubility of different compounds. Now, solubility is directly proportional to ionic size. As size increases, solubility also increases. How do we explain that? So, as the ion gets larger, more water molecules can surround it. So this means that the AB interactions get larger, right? So the AB interactions become more favorable. And that's what increases the solubility of the compound. So let's look at these examples between potassium fluoride, potassium bromide, potassium chloride, potassium iodide, which would have the maximum solubility. Well, the size of the iodide ion is the largest. You're comparing the same potassium ion, so that does not have any effect here. So because iodide is the largest ion, Ki would have the highest solubility. Now, ionic charge works slightly differently. Solubility is inversely proportional to ionic charge. As charge increases, solubility decreases. How do we explain that? Well, in this case, as the charge increases, what happens? The solute particles, so we're talking about water as the solvent, so if the charge is higher, the solute particles are held more strongly with each other because the charge is larger. So this means the AA interactions get higher. So if the AA is higher, AB would have to be much more higher to allow for solubility, right? So that's why solubility would decrease. Let's look at some examples. So between sodium hydroxide and aluminum hydroxide, so you have the same anion, which would have higher solubility. Well, aluminum has the higher charge, 3+. So this means that aluminum hydroxide, the AA interactions are higher here. This would have lower AA interactions, which means this sodium hydroxide would have the higher solubility. Similarly, between potassium fluoride and potassium oxide, so these two are the same. You're looking at the charge here. So this is the fluoride is 1 negative, oxygen is 2 negative. Again, the AA interactions would be higher here and lower here. This would have more solubility. So this is looking at water dissolving ionic compounds. What about water dissolving other polar compounds? So polar compounds would dissolve in water due to hydrogen bonding. So let's look at something like methanol. So you've got the, I'm just drawing it as one functional group, oxygen, hydrogen. Again, you've got the two lone pairs on oxygen. So this has a slight negative and this has a slight positive character. So this could again dissolve in water with the similar idea of hydrogen bonding with the negative end of water, so which is the oxygen, right? So being attracted to this side, and here the positive hydrogen end would get attracted to this side. Okay, so this could dissolve in water as well. If I show the negative, the positive. This is very hard. I don't like the video lessons. Okay, how do we predict this solubilities of these different compounds? So you don't need to know the names. Again, this is something you would learn in grade 12. So you've got methanol, ethanol, propanol and butanol. So you've got 1 carbon, 2 carbons, 3 carbons and 4 carbon. As the size of the non-polar end increases, so as this chain gets larger and larger, solubility decreases. Okay, so this would have the lowest solubility and this would have the highest solubility. And again, you can explain the reason by this is the only polar end. You have the exact same polar end on both on all 4 of those molecules. As the non-polar part increases, it gets harder and harder for water molecules to surround the only small polar end available on these molecules. The opposite would be if you had more OH groups on these carbons, then the solubility would increase, because now the number of functional groups, the number of functional polar groups that can form hydrogen bonding with water is increasing. Okay. Let's look at the case of polar and non-polar. So again, if we are talking about water, the polar would be the water would be the solvent, and the non-polar would be the solute. In general, polar and non-polar substances would not mix with each other, owing to the fact that the polar substance sort of is attracted to each other by these electrostatic forces of attraction. They would tend to stick together and would not mix with your non-polar solute or solvent, whatever is coming in. So there is no interaction here that can overcome the breaking of these polar interactions. So polar and non-polar would not mix with each other. What about non-polar and non-polar? Well, they don't have any electrostatic forces of attraction on both sides. There's no hydrogen bonding. Whatever non-polar attractions are on this side, van der Waals forces would also be with when they're both mixed. So yes, non-polar and non-polar will mix with each other. Okay. And then the last thing mentioned in 8.2 in the book talks about soaps and detergents. So soaps have both ends. So they've got this non-polar hydrocarbon chain and they've got this polar end. Soaps are usually sodium or potassium salts of fatty acids. So what these molecules are called, so this is the hydrophilic, and philic means loving. So this is the water loving end. This is the hydrophobic, the water hating end. Phobic is to fear or hate. So this is the water fearing end, water loving end. Something like this, a molecule that has both of these ends is called amphiphilic, which means it likes both. It likes non-polar and it likes the polar ends. So this property is very useful in the case of soaps. What happens is that the non-polar end of the soap molecule attaches itself to non-polar fats and dirt. So if I said there was a dirt particle, right, and let's say this is non-polar, I don't know if that shows, yeah. So this is non-polar. You cannot dissolve this fat or dirt in water because water is polar, and we said that only like dissolves like. So what you do is you get this non-polar hydrocarbon chain from the soap is attracted to this dirt particle. And again, if you're thinking why the chain is shaped in this way, that goes back to geometry. So we did that in unit 1. If you actually look at those hydrocarbons, when you arrange the carbon and the hydrogen, this is the shape that they would take. So the non-polar end is attracted to this non-polar dirt, and then the polar end, which is sticking outside, so I'll draw that in red, can now be surrounded by water. Okay, so you have a layer of, you have your dirt inside or fat, you have your soap, the non-polar end of the soap, and then all of this in turn is surrounded by water molecules. So I'm just going to say, show kind of an envelope of water molecules. So this will be your water. So this is how soaps can clean your clothes, your hands, anything you've got there, by the fact that they're amphiphilic. They like both the non-polar dirt and they like the polar water. So this whole I'm looking for a word, together is called a myceli. So I've heard different pronunciations, myceli or micelle, whichever one you like. So you've got this whole thing, and this, as you agitate your cloth or your hands, when you rub your hands together using more water, this myceli can be dissolved in water and is washed away. So if you remember that demo in class where we had some water in a plate, pepper particles were able to float on top of the water, demonstrating the surface tension in water. But as soon as you take a little bit of detergent on your finger and you put that in the middle, this detergent is able to break through the surface tension of water. Such molecules are called surfactants, those that act on the surface and reduce surface tension of liquids. Okay, so detergents are also known as, soaps and detergents are also known as surfactants. You can read these pages in the textbook, and then I think the next part we haven't covered with the rest of the class yet, so I will do that in class. But there were problems to try from the textbook 8.3. We will take these up in the next class. So that's pretty much what we did in the class that you missed. Hopefully you can join us for the next class on Wednesday.